We are diving straight into live avatar, streaming real-time audio-driven avatar generation with infinite length.
And this one is a big deal. We're talking about making massive diffusion models, like 14 billion parameters, actually usable in real time.
Which has always been the dream, right? But the problem is that classic trade-off between scale and speed. These huge models give you incredible fidelity, but they're just so slow.
Exactly. The whole denoising process is sequential, which creates this crippling latency. You can't get anywhere near the 20 frames per second you need for something to feel live.
And that's just one side of the coin. Even if you could get the speed, you get this weird consistency problem over time.
The identity drift, the avatar just sort of slowly changes, or the colors get weird. It's a huge issue for long-form streaming.
So this paper, Live Avatar, it presents a framework that, kind of amazingly, solves both problems at once.
It does. For speed, they hit over 20 FPS using something they call Timestep-forcing Pipeline Parallelism, or TPP. It's a whole new way of using the GPUs.
And for that consistency problem, they introduced the rolling sync frame mechanism, the RSFM. This lets them generate video for what they call infinite length.
And they actually tested it up to 10,000 seconds. It's just rock solid.
So, bottom line, this is probably the first time a 14 Lie parameter model has been made truly practical for real-time, high-fidelity, long-form video. It really sets a new bar.
It really does. It moved these massive models from a theoretical best quality to an actual deployable product.
Okay, let's unpack those core challenges a bit more, because the solution is so much more impressive when you understand just how hard the problem is.
Right.
You mentioned that real-time fidelity dilemma. Why can't you just use normal parallelization to speed up a 14B model?
Well, it's because the diffusion process itself is the bottleneck. It's inherently sequential. You have to finish denoising step T before you can even start step T-1.
It's a dependency chain. You can't do step 2 until you finish step 1.
Exactly. You can't run the steps themselves in parallel. And when you have a bunch of steps, that time just adds up and your frame rate plummets. I mean, we're talking way below 1 frame per second for models this big.
So people would use smaller models like 1.3B to get the speed up.
But then you sacrifice all that amazing detail and quality. It's a classic catch-22.
So that's the speed wall. And then you hit the second wall, which is the long horizon consistency. What's actually happening under the hood that causes that drift?
It's basically a slow accumulation of tiny errors. Each frame you generate is used to help generate the next one, and if there isn't a really strong, stable anchor...
the errors just compound.
They compound, exactly. The avatar's face might shift a tiny bit, the lighting changes, the colors wash out, and over a few minutes it becomes really noticeable and distracting.
So the goal was clear. Get the quality of a 14B model, but make it fast enough for streaming and stable enough to run, well, indefinitely.
And they realized pretty quickly this wasn't just an algorithm problem. You couldn't just invent a clever trick. It had to be a total co-design of the system and the model from the ground up.
Let's get into that. The model adaptation part is fascinating. They had to take this huge non-causal model and basically teach it how to think sequentially for streaming.
Right, and it's a two-stage training process. The final model works autoregressively, meaning it predicts the future based on the past, but it generates in blocks of 3 frames at a time.
And it conditions that generation on a few things, right? The audio, a prompt.
And 2 critical memory sources. The short-term memory, which is the key value cache, or KV cache, from the last few blocks.
So that's like remembering recent head movements and what the mouth was just doing?
Exactly. And then there's the long-term identity anchor. They call it the rolling sync frame, which is basically the permanent reference for what the person should look like.
The ID photo, got it. So stage 1 of training is this diffusion forcing pre-training.
Right. This is all about getting the model stable before the really intense training. And the key here is a causal local attention mask.
Which sounds complicated, but it's really just enforcing that past predicts future rule, isn't it?
That's all it is. It lets the model pay full attention to everything within the current 3-frame block it's generating. But when it looks back in time, that mask ensures it only sees things that have already happened. It forces it to learn causality.
Which then prepares it for stage 2, self-forcing distribution matching distillation, SFDMD.
Bit of a mouthful.
Just a bit.
Yeah.
But distillation is all about speed, right? You take a slow, brilliant teacher model and have it teach a smaller, faster student model how to get the same results.
That's the goal. So they have the big, slow, high-quality teacher model, a fake score model that's being updated, and then the actual student, the fast, few-step causal generator. The whole process is about closing the gap between what the student produces and what the teacher would have produced.
And this is where they do something that sounds completely backwards at first. The history corrupt strategy. They intentionally add noise to the historical KV cache. Why on earth would you corrupt the model's memory while you're training it?
It sounds so counterintuitive, I know. But it's actually a brilliant way to build robustness. By forcing the model to generate a perfect new frame, even when its short-term memory is a little fuzzy or corrupted.
You force it to rely more on the stable, long-term anchor?
Precisely. It learns to distinguish better between the noisy, temporary motion cues in the KV cache and the clean, permanent identity cues from that sync frame. It makes the model incredibly resilient to degradation over time.
That's really clever. And their ablation study on this turned up another key insight about noise levels, the whole time step forcing thing.
Yeah, this was fascinating. The traditional way is to use a clean KV cache, so the historical memory is always pristine. They compare that to their method, time step forcing, where a noisy latent at, say, step T is attending to a historical cache that is also at noise level T.
And it wasn't just more efficient.
It was better. It produced higher perceptual quality scores. It turns out that aligning the training this way matches how diffusion models inherently want to learn by comparing things at similar noise levels. So it was a win for efficiency and a win for quality.
Just a beautiful, elegant result. Okay, so the model is now causal and super robust, but we still need the raw speed. That brings us to the hardware side. Timestep-forcing Pipeline Parallelism, or TPP.
This is where they completely changed the game. The sequential denoising process seems like an unbreakable chain, but they figured out how to break it.
How?
They reframed the problem. Instead of trying to parallelize the model, they parallelized the process. Think of it like a factory assembly line.
Where each worker does one specific task in sequence.
Exactly. They take, say, 5 GPUs, and instead of each GPU trying to do the whole process, they assign each GPU just one single fixed denoising step. So GPU 1 only does step 5 to 4, GPU 2 only does step 4 to 3, and so on down the line.
Wow. So you turn the time-based sequence into a physical spatial pipeline.
And that completely changes the math for throughput. After a short warm-up period to fill the pipeline, the speed is no longer limited by the sum of all the steps. It's only limited by the single slowest step on any one GPU.
Which is how they hit that 20.88 FPS. It's just maximum parallelization.
It is, and it's incredibly efficient. Because each GPU is dedicated to one time step, it only needs to keep its own small local KV cache for that specific noise level.
So you don't have to do all that slow, costly communication of the giant KV cache state between the GPUs.
You don't. You just pass the much smaller latent tensor down the assembly line. It's a brilliant bit of system design.
And they even thought about the final bottleneck, the VAE decoding.
Right. Turning the latent back into an image takes time, and that could stall the whole pipeline. So they just offloaded that to another totally separate GPU.
Keeping the main pipeline flowing at maximum speed, the ablation study really says it all here. Without TPP, the FPS drops from over 20 back down to, 4 or 5?
It proves that this co-design, this TPP system, is the absolute key to making a model this large run in real time. It's not an optimization, it's the core enabler.
So TPP solves speed. Now, for the consistency, the rolling sync frame mechanism, or RSFM. This tackles the two big enemies of long-form generation, inference mode drift and distribution drift.
Let's start with distribution drift. That's when the model starts generating weird colors or styles, maybe because the original reference photo you gave it is just a little bit outside of what it's comfortable generating.
So how does the adaptive attention sync, AAS, fix that?
This is such a cool self-correcting idea. As soon as the model generates its very first frame, it takes that frame, encodes it, and uses that as the new permanent reference, throwing the original photo away.
Oh, wow. So instead of being anchored to an external, potentially weird photo, it anchors itself to its own best work.
Exactly. It anchors itself to a frame that is, by definition, perfectly within its own learned distribution. This locks in the color and style and prevents it from ever drifting into unrealistic territory. It's like self-calibration.
That's brilliant. And then to stop the face itself from slowly morphing over time, the inference mode drift, they use rolling rope. What's rope?
Rope-E is rotary positional embedding. It's how the model knows how old a piece of information in its memory is. The problem is, if your sync frame anchor gets infinitely old, its influence can fade, leading to drift.
So rolling rope-E is like a way to keep resetting the clock on that anchor.
That's a perfect way to put it. It dynamically adjusts the positional offset so that, from a model's perspective, the sync frame always appears to be at the optimal distance to provide a stable identity reference.
So it doesn't matter if you're at second 10 or second 10,000, the anchor always feels like it's right there.
And that provides that unshakable long-range identity without messing up the local short-term motions for lip sync.
And the proof is in that wild extrapolation test. They trained it on 5-second clips and then just let it run for 10,000 seconds straight.
Nearly 3 hours. And the results are just flat. The quality metrics, the sync scores, the consistency scores, they're practically identical at the 3-hour mark as they were in the first 10 seconds. It's an incredible demonstration of stability.
So let's talk about the final numbers, how it stacks up against other SOTA models. On the Gegenbench long video benchmark, it just blows past things like Ditto or Omni-Avatar.
Especially on the metrics that matter for long videos, like visual quality and semantic consistency over time. It just degrades so much less than anything else.
And the speed metrics are, frankly, not even a fair comparison, 20.88 FPS.
I mean, the other 14B models they compare against are running at less than 1 FPS, sometimes 0.16. So live avatar isn't just a bit faster, it's literally 100 times faster in some cases. It's in a completely different category.
And they still get a pretty good time to first frame, under 3 seconds, so you're not waiting forever for it to start up.
But the part I found most compelling was the human perception study, because the raw numbers don't always tell the whole story.
Right. They tested for naturalness, synchronization, and consistency. And this is where you see some models trying to game the test.
Yes, exactly. So a model like Omni-Avatar gets a really high objective score for lip sync, for sync-C. But humans who watched it rated it as very unnatural.
Why is that?
Because to get that high score, the model was exaggerating the lip movements, making the person look really strange and hyper-articulated. It looks right to the math, but it looks wrong to a human eye.
And this is where live avatar really shone. It got the highest scores from humans for both naturalness and for consistency.
It proves that their approach, like the history corrupt strategy and the RSFM, created an output that wasn't just technically correct, but felt perceptually authentic to people.
They didn't just solve the engineering problem, they solved the user experience problem.
That's a great way to summarize it. So putting it all together, Live Avatar really does bridge that gap. They use TPP for the real-time speed and RSFM for that long-term infinite-length fidelity.
It's a complete package.
Yeah.
Real-time, 20 FPS streaming from a 14B model with proof of consistency for almost 3 hours.
They did mention a couple of small limitations, to be fair.
Of course.
The TPP strategy is amazing for throughput, for FPS, but it doesn't dramatically reduce that initial startup time, the time to first frame, because you have to fill the pipeline.
So it's not truly instantaneous.
Not truly. And they also note that the RSFM, while amazing for talking heads, might have its limits in really, really complex scenes that are way more dynamic.
Still, the core idea of using the model's own output, that first generated frame, to correct itself is just revolutionary. It shows self-referencing can be more powerful than a static ground truth reference.
It's a fundamental shift in thinking about consistency.
Absolutely. And that leaves us with a final provocative thought for you to chew on. We've seen that the model can use its own generated distribution to correct things like color and style drift. So what happens when you extend that? What happens when you let the model incrementally correct and re-reference other persistent features in a scene?
Like the background geometry or the texture of someone's clothes or how a shadow falls.
Exactly. Could that kind of continuous, iterative self-correction be the key to generating truly stable, long-form, fully immersive virtual worlds, where everything is generated moment to moment, but everything also stays perfectly consistent over time? What would that unlock?